Hey AP Physics C kids, in this video we're going to look at electric fields for rings of charge. So let's go. So a couple tips when we do our integration here to add up all of our little pieces of charge across this charged ring, we want to replace our r in our 1 over 4 pi e naught dq over r squared in terms of the variables given, like z, which for this case is the distance to point P from the center of the ring, and the radius, which is the distance from that axis out to the ring itself. Because if we look at this, right, we're going to have electric field at angles again, so we're going to have to split them into x and y components. We're going to want to replace theta in terms of those constants as well, our z and our r. Now, there are two things. If the total charge is q, then you can just leave it as dq and set your limits from 0 to q, because if you think about it, z and r, right, these guys are constants. So we don't have to integrate over that because they're not changing. Or if you have a linear charge density, then you'll replace dq with lambda ds. Before it was lambda dx, right, when we did the linear ones, and we'll integrate s around the circumference of the disk. So either way, you can do either one, honestly. But if we're given q and r and z and whatever, we might as well just integrate from 0 to q. But, you know, depends. Sometimes you'll get a nonlinear charge density, and then we have to go with lambda ds. All right, so let's get going. So our electric field is 1 over 4 pi e naught integral of dq over r squared. Notice I already pulled out the 1 over 4 pi e naught. Why not? Okay, now in this case, our electric field is actually at angles, right? Every place along here, if I go up a distance r, it's going to be pointing in that direction. It's going to be a 3D kind of phenomena. It's going to make kind of like an inverted cone as we go around. But the cool thing about that is that the electric field in the x direction, which would be the adding up of all the E, would be sine theta, is going to cancel out. And I say sine theta because we're going to use this theta right here like we did when we had the electric field for the off-axis line of charge. So our net electric field is going to be in the y direction. So we're going to add up all of our E cosine thetas. And that's going to give us our net electric field. So, net, I almost wrote Ned. So that means that our net electric field is going to be 1 over 4 pi e naught, the integral of dq over r squared times the cosine of theta. And that's only because the x components cancel out. If they didn't, we'd also have to do an integral of the electric field at the sine of theta. But fortunately for us, not the case. Now, like I said, we want to replace r and cosine theta in terms of the variables, so we get them all into the same sort of units or variables. And so r, which is our distance from the little piece of charge we're going to add up here on the ring to point P, we can write that, we can make a right triangle here, and so we can say that r is equal to the square root of the radius squared plus z squared. Now, this is z, I wrote z here, but it could be y, it could be a, it could be anything. So whatever this distance is from the center of the ring to the point of interest. Our cosine of theta is going to be the adjacent here, which is that z, over the hypotenuse, which is our capital R squared, our radius squared, plus z squared, square root of that. Okay, so we can go back over here and we can enter that stuff in. So our net electric field, which is the y direction, is going to be, or the z direction, I don't know, whatever you want to call that. The vertical, upward direction is 1 over 4 pi e naught, integral of dq over r squared, which is going to be the radius squared, plus z, the distance to point P from the center, times the cosine of theta, which we're going to express in terms of z, and our hypotenuse r, which is the square root of capital R squared, radius squared, plus z squared. Now, z, r, right, those are constants. Those aren't changing. We're not adding those things up. We're adding up the q, which means that we can pull all those constants out. So my net electric field then is z on the top over 4 pi e naught, which of course you could also write as k if you wanted to. And then on the bottom here, if we combine these two terms, we're going to get r squared plus z squared to the 3/2. And then we're just going to do an integral of dq from 0 to q. Well, the integral of dq is just q, so that's just z over 4 pi e naught r squared plus z squared to the 3/2, not 32, to the 3/2, and then that's just q, because it would be q from 0 to q, which would be q. So that means I'm just going to put a q up here. Wow, that's it. Or of course you could write it in terms of k, so we'd have k, I'm going to put the q first just because I like q first, z over r squared plus z squared to the 3/2. Either of these would be an acceptable answer. It's in terms of the variables given. It doesn't say z on here, but and that is a z. It looks kind of like a 2, based off the picture I'm given. Now, the problem should probably say a distance z away from the center of the ring. And the problems you get will say that. Now, I do want to do this one more time, but instead of doing q, I want to replace q, or dq, I want to replace it in terms of lambda ds. And I want to show you how that works, just in case we ever get a nonlinear charge density or you get a lambda. So we're going to go through, I'm just going to skip this ex stuff right here, and we're going to go right here. So actually, we're just going to take this here, move this down here, and then instead of dq, I'm going to put in lambda ds. And I'm going to pull all the constants out. Maybe I should have started here. I don't know. Anyways, the net electric field is, we've got our constant z. We have our 4 pi e naught. We have our r squared plus z squared to the 3/2. So that doesn't really change. But this is what changes. Instead of our dq here, we're going to write in terms of lambda ds. So lambda, of course, is a constant. So let me rewrite that out there. So we've got lambda z over 4 pi e naught r squared plus z squared to the 3/2, and we're going to integrate ds. Our limits, since we have a full circle here, our limits are going to be from 0 to the circumference of the disk, which is going to be 2 pi times the radius. Once again, the integral of ds is just s. We're going from 2 pi r to 0. So if I write my final answer here, we would have our constants, our lambda, we'd have our z, we'd have our 4 pi e naught r squared plus z squared to the 3/2, and then this would be 2 pi times r, because the integral of ds is just s from 0 to, or from 2 pi r to 0, or whatever, minus 0, so the 0 goes away. And of course we can simplify this. We can get rid of this 2 pi, we can get rid of that, make it a 2, and so that would be lambda zr over 2 e naught r squared plus z squared to the 3/2. Now, if you did this in terms of k, it would be different, right? If you did it in terms of k, then you wouldn't be able to get rid of the 2 pi on top and simplify the 4 pi on the bottom. So it would look a little different if you did k, but you could have done k as well. But if you have a lambda, it's going to look like that. And of course, you could still do it in terms of lambda, and then lambda, right, for the total ring would be q over 2 pi r. So if we put this in for our lambda, you're going to notice that you're going to get the same thing you got up here. So funsies. All right. So that is a ring of charge. Not too bad, right? I like that kind of integral. All right, that's enough for this.